this is Sayyid Raza Mashhadi and welcome back to the channel. This is session 8 of electrical resistivity tomography from 0 to hero, and in this session I'm going to talk about checking the reliability of ERT inversion results. This is going to be important, so let's start. We focused on suitable selection of inversion parameters as a prerequisite for having a reliable resistivity or IP model, and we have discussed that after having the resistivity model we're going to face the question that is our model reliable or acceptable or not. And in this session I'm going to address this question, and I have to say that the inversion results should not be trusted all the time before being checked. So it is important to check them, especially if you're dealing with a noisy dataset or with a problematic dataset. So this is going to be important for you if you're working with challenging datasets. After running the inversion results must be checked to ensure that first, the model is mathematically reliable and correct, and then second, it is the best possible estimation of subsurface resistivity distribution. I know that we have to consider some facts about the resolution of our dataset, etc., etc. I don't know, smearing out with depths in some situations, but overall our goal is to provide a realistic, good representation of the subsurface resistivity distribution or IP distribution in terms of IP. So we have to be sure that the model is reliable and it is the best estimation. This discussion is going to be extremely important for problematic noisy datasets, as I stated, and that's important because it gives you the opportunity to reprocess your data, do some pre-processing again, and selecting the inversion parameters in a different way to yield better results. So this is very important. Let's go to the next slide, and here are 4 points that shows us a few tips regarding checking the reliability of the inversion results. The first one is that the model of subsequent iterations must be similar in terms of general subsurface features. This is very important, and mostly if you have been working with good datasets, you see it all the time, and it must not be very a specific point for you, but in terms of problematic datasets, this is a very important fact to consider, and this is a first checkpoint for you to tick if you're going to say that my inversion is going to be reliable in terms of mathematics. So this is the first one. The second one is the error of subsequent iterations should follow a declining trend. If it increases again from a specific iteration and then it decreases, it is not going to be good and reliable. So if it increases from a specific iteration, the rest iterations are not valid. That's it. Even if the rest of the iterations provide much more lower RMS errors. That's it. That's in terms of mathematics. Mathematic reliability of the model. The point 3 is that if the model of subsequent iterations are exactly similar, while the RMS error decreases a little bit and the range of resistivity IP values in fact is changing dramatically, it indicates the effect of data overfitting. So let's state it again. If we are facing in a situation that the subsequent iterations are just getting lower in terms of RMS error, but the picture of the inversion is similar in subsequent iterations, the model is similar, but the only thing that changes is the range of resistivity and IP values. So for example, in the iteration 5 and iteration 6, we have in iteration 7 we have similar patterns of resistivity or IP, but and the only thing that is variable is their ranges and the RMS error decretion or decline. In this case, this is indicative of data overfitting, and data overfitting is an important thing to consider, especially if you're going to in fact, and we are going to use the values of the models to interpret the models, and if you're going to use some kind of clustering techniques, so they will be problematic. So data overfitting must be known, and it should not be just taken okay because of a lower RMS error. So also check if you're facing with data overfitting in your inversion or not. The fourth point is that you should avoid using too many iterations for field data. That's it. I have seen people using 8 iterations, 10 iterations. That is not the way to go. In restivity and using the proposed, prepared inversion routine, it is not good to use too many iterations. You can use too many iterations, 10 iterations, 8 iterations, just for synthetic data sets that are noise free. In the data of the field, the data of your study area that you have gathered have some levels of noise. So you should not adopt too many iterations to gain a lower RMS error. So this is a fact to consider. So if these 4 points are checked, you can say that my inversion models are reliable. And here is an example. This is an example from a very good data set, relatively good data set, and you can see I have provided the RMS errors of resistivity and IP together with the color scale of the different iterations. And if you want to show the different iterations in REST2D or REST2D in software, you have to use page up and page down buttons on the keyboard. So if you look at this, you will see the general picture is the same. We have a low resistivity values in here, that is the sedimentary cover, and in here we have some geological units, volcanic units that have higher resistivity values, and then iteration after iterations the model is getting better in terms of details. So for example, in here you will see that this feature that was not in fact linked here is just linked, and the exact value of the resistivity is in fact getting closer to the best estimation, and the general pictures, general theme of the resistivity values are similar, and you can see the decrease of the RMS error from 8.56 to 3.05, and this is a very fine inversion, and we have checked that we are not facing any in fact overfitting, because the data is not changing totally in a way that we have extremely high or extremely low resistivities, while the models are similar, and you can see some little differences in these models, the second and fourth iteration values, and also the RMS error. So both of iteration 3 and iteration 4 would be good options to pick as a final model, but the iteration 4 is a little bit more precise and features a little bit more detailed reconstruction of the subsurface that is much more realistic, because we have some geological units that dip in this way, so you see that these counters are just having these shapes in here. And so the iteration 4 is going to be better than iteration number 3. Although both of them could be the best and could be a good option to use as the final model. Please remember that the tips mentioned here are somehow related to the mathematical correctness of inversion, if you can call it like that. And it is always recommended to check models with other geoscientific data and information as well, like geological maps, geological cross-sections, I don't know, satellite imagery, whether it is helpful for detecting, I don't know, some features like faults, I don't know, pollutions, everything that could be useful. And in this second tip, we check the realisticness of our model, in addition to the mathematical reliability. And also, again, emphasizing on the point that the lower RMS error is not the only thing to consider, and because it may be the problem of non-uniqueness, in which we have a model with lower RMS error, but it is related to one of those million possibilities that fit our data that is not going to represent the true geology or the true subsurface distribution of resistivity. So always check for the correctness of your inversion models in terms of mathematics and realisticness. And that's it for this session. Thank you and have a nice day.